This video will demonstrate how to install and begin using GCPy, GEOS-Chem's Python toolkit. GCPy provides many functions for plotting, tabling, and regridding GEOS-Chem's netcdf input and output. In this video, I will show you how to set up a Conda environment for working with GCPy, how to install GCPy itself, and how to perform a few of the main operations that GCPy supports. More extensive documentation on both the setup and usage of GCPy is available on our Read the Docs site, shown here on the left, which is linked in the description of this video. I would also like to clarify that GCPy is currently only supported for Mac and Linux operating systems. I'm recording this video on a Windows machine, but all of my work in this video with GCPy takes place on a Linux machine, which I'm remotely logged into from my Windows home desktop. With that out of the way, let's talk a bit about GCPy and its intended uses. GCPy is a Python-based toolkit containing useful functions for working specifically with the GEOS-Chem model of atmospheric chemistry and composition. GCPy aims to build on the well-established scientific Python technical stack, leveraging tools like CartoPy and Xarray to simplify the task of working with model output and performing atmospheric chemistry analyses. In creating GCPy, we are not reinventing the wheel that is the scientific Python technical stack. GCPy has specific functions to make working with GEOS-Chem data easier and more efficient, but does not capture all Python usage scenarios you may encounter as a GEOS-Chem user. There are many Python packages that GCPy is built off of, such as Xarray, CartoPy, and Matplotlib, which you may want to use independently of GCPy to better serve your specific needs. We are happy to add both new functionality to GCPy as well as new examples on this Read the Docs website. You can use our GitHub issues page to request new features or examples, and can also open a pull request if you create any examples or code additions of your own. The URL to the GCPy GitHub page, as shown here on the issues page, is listed in the video description below. So to get into the intended uses of GCPy, you can use GCPy to produce plots and tables from GEOS-Chem output using simple function calls. The plot on the right is example output from a series of GCPy function calls showing surface ozone concentrations in two GEOS-Chem species concentration output files. GCPy is also used to generate the standard evaluation plots and tables from GEOS-Chem benchmark output. This is an important use for the GEOS-Chem support team as we prepare each new version of GEOS-Chem. General users can use this functionality to generate comprehensive plots and tables for their own GEOS-Chem runs. GCPy also holds information about GEOS-Chem's horizontal and vertical grids, and can be used to regrid restart files and data for plotting between cube-sphere and lat-long horizontal grids. Finally, GCPy provides example scripts for creating specific types of plots or analysis from GEOS-Chem output. These examples are provided in the example script section, as shown over here, of this Read the Docs site, and can also be found in the GCPy Git repo. So those are the main usage categories for GCPy. As I mentioned earlier, there's also some tasks you may want to perform using GEOS-Chem output that GCPy just isn't intended to do because there are existing well-suited tools for the job. These include, but are not limited to, general netcdf file modification, for example cropping your vertical or horizontal domain or extracting some specific variables from a dataset. Xarray is a great Python package for doing general work with netcdf files, and we also have a page on the GEOS-Chem wiki that lists other tools for working with netcdf files. GCPy also has no direct support for statistical analysis. You'll want to use Python packages like SciPy and scikit-learn instead. On a related note, GCPy has no direct machine learning functionality. There are several standard utilities both in and outside of Python that you can use to set up machine learning with GEOS-Chem data. So that sums up the usage cases for GCPy. Now we'll get into how to install and use GCPy. There are two different ways of installing GCPy, depending on whether you intend to modify the source code of GCPy or if you want to simply use the different modules included within GCPy. In this video, I will show you how to install GCPy without intending to modify GCPy's source code, but instructions for installing the other way and the way demonstrated in this video are included on the Read the Docs site. The first step to installing GCPy is to first install a distribution of Conda in the form of Mini-Conda or Anaconda. Mini-Conda is much more lightweight and functions perfectly well for GCPy purposes. while Anaconda automatically includes many extra packages that are not directly relevant to GCPy. In this video, I will be using Miniconda. The installation process for Miniconda in a Linux terminal is quite simple, and as I mentioned, installation instructions for both Miniconda or Anaconda for different operating systems can be found on the Conda Read the Docs site. Here in this terminal, all I need to do is download a distribution of Miniconda using wget, and then simply execute the install script and then follow the prompts that it gives me. Once you have installed Miniconda or Anaconda, you can begin using Conda commands from the command line. The next step is to create a Conda environment for working with GCPy. To do this, you will type conda create and then -n to signify the name of whatever you want to call your environment. I'm going to call mine GCPy demo, and then it will create this environment. It shouldn't take too long because you're not going to be installing too many new packages when you make it. Simply accept the prompts it gives you. And now this environment exists, and to enter your environment, simply type conda activate and then the name of whatever you called your new environment. In this case, GCPy demo. Once you have created and entered this Conda environment, you can install GCPy directly from Conda. Conda will handle the installation of all the dependencies for GCPy automatically. Most dependencies have minimum version requirements. When installing GCPy through Conda, Conda will ensure that all installed dependencies use versions that are compatible with one another and with GCPy itself. A full list of package version requirements can be found in the environment.yaml file contained in the GCPy Git repository. To install GCPy from Conda, you will need to add the Conda forge channel to the list of places from which Conda can fetch packages. Once you've added Conda forge to your list of channels, simply type conda install GEOS-Chem -GCPy. It might take several minutes as it finds compatible versions for each of the dependencies, but make sure you follow the prompts that it gives you, and in the end you'll have an installation of GCPy. Once this installation process is complete, you will now be able to use GCPy from within the Python interpreter or from within any different Python scripts you want to execute. To test that your installation of GCPy was successful, you can go into your Python interpreter by simply typing Python in the terminal and then typing import GCPy. This may take a couple seconds as it wants to import all the different modules which GCPy depends upon, but it should complete successfully and your installation has likely succeeded. So now I'm going to briefly go over the different capabilities of GCPy, the first of which is plotting, which I'll show a few examples for in the end. So there are two main types of plots in GCPy. There are single level plots and zonal mean plots. This is a single level plot of a single vertical level in the atmosphere in single panel format, meaning that it's taking a single variable from one GEOS-Chem dataset and plotting it on a single map. The other main type of plot that we create in GCPy is the zonal mean plot, which shows values for some quantity, in this case ozone, averaged across latitude bands throughout different layers of the atmosphere. This is again a single panel plot that we've created here, but there is another format that we also tend to create in GCPy. This would be the 6-panel comparison plot. In this case, I'm showing a 6-panel plot of surface ozone across the globe at a single time step from two different species concentration files from different GEOS-Chem runs. The run on the left is a GEOS-Chem classic run, and the run on the right is a GCHP run. Each of these 6 panels plots a different quantity comparing the data from each of these runs. The top left panel shows the species concentrations of ozone at the surface for our GEOS-Chem classic run. The top right panel shows the same thing but for the GCHP run, and the bottom 4 panels show different quantities that are differences between the GeoS-Chem classic values and the GCHP values. Notice that although the run on the left is on a lat-long grid with a 4x5 resolution, and the plot on the right is from a run with a C48 resolution in cube sphere format, that these different data sets are able to be compared in these plots. This is a capability that you do not need to handle on your own. GCPy will handle plotting across different grid resolutions and types. In this case, GEOS-Chem has chosen a lat-long grid of 1 by 1.25 degrees to compare the two data sets. The middle left panel shows the absolute difference between the values plotted in the top left and top right using a dynamic color scale, while the middle right panel shows the same quantity but uses the 5th and 95th percentiles to bound the color scale. Like the middle row of plots, the bottom row of plots also shows differences between concentrations of surface ozone from the two data sets, except the bottom row shows the data sets divided by one another, with the bottom left plot showing the dev data set divided by the ref data set, which in this case is the GCHP data set and the GEOS-Chem Classic data set, respectively, and uses a dynamic color scale, while the plot on the right shows the same quantities but uses a restricted color scale from values of 0.5 to 2. 6-panel plots can also be generated in zonal mean format. When generating either 6-panel or single-panel plots, you can choose to create interactive figures, or you can pipe all of the figure output directly to PDFs, which you can specify by name in the function calls. As I mentioned earlier in this video, you can use GCPy to generate comprehensive plots of GEOS-Chem output. You can also use GCPy to generate different diagnostic tables showing different quantities, such as budgets for different species according to different operations, as well as global mass of different species in different regions of the atmosphere, or total mass of different emissions emitted over the course of one of your GEOS-Chem runs. I also mentioned earlier how GCPy will automatically handle regridding when plotting between different horizontal grids. You can also regrid between different vertical grids when plotting, which is automatically handled if you're using the 72 level or 47 level vertical grids that are predefined in GCPy. You can also use GCPy to regrid GEOS-Chem restart and output files between different resolutions and grid types, such as latitude, longitude, standard cube sphere, and stretch grid. Now I will do a live demonstration of how to create the different single panel and 6-panel plots that GCPy is able to generate. And you can also find other examples of different plotting and tabling abilities on the Read the Docs website. So the first thing I'll demonstrate is creating a single panel, single level plot. So the first thing we'll do, go into our Python interpreter, import Xarray so we can open up our netcdf files, import the plotting module from GCPy, call that gcplot, and make sure we can actually forward our plots via X11 forwarding and be able to see them without creating a PDF using matplotlib's pyplot. So then we'll open up our species concentration file. This is a file from a 1-month run of GEOS-Chem Classic from 2019 July. And we can take a look at the different data variables we actually have in this file if you just print out the data variables attribute. And we're going to end up plotting methane, but you can see it's got all the different species from this run included, plus some other variables. So now we're going to only select methane by indexing into our new Xarray dataset, get methane. Then we only want to look at the surface, so we will index into that data array and only look at the first level with index 0. And now we can do a really simple plot using only one argument to the single panel function in the plot module, and that would be the actual data array. And it'll spin for a minute, and we'll then take a look at what it actually looks like. Or some fun gobbledygook from X11. And we still get an actual visible image. Great, so this shows methane at the surface across the whole world because we did not give it a specific region and this was a global file. We can see it by default will give the image a title with the name of the data variable we're using. It chooses a color map automatically, but you can specify your own. And yeah, there's a bunch of different arguments that I'll get into now that you can also specify to customize this sort of plot. So now I will demonstrate creating the same plot but with a couple extra specified parameters. So we'll again do gcplot.singlePanel, use the same array of data, specify a new title. We'll call it Surface Methane over the North Pacific. Specify a color map. We're going to use the Viridis color map. And specify extent that we actually want to plot. So we're going to specify a leftmost longitude, rightmost longitude, southernmost latitude, and northernmost latitude. Great, so that'll generate, and we'll go to show the figure, and I want to clarify again that these are not relevant error messages to GCPy itself, they're due to my X11 setup. And great, now we have the same plot we did before, but not quite. We've zoomed in on a specific region, in this case the northern part of the Pacific Ocean, and we've changed the color map and we've added a new title. So that's a summary of using the single panel function. There's more details on this function and all other functions on the Read the Docs site. So now we've generated a PDF containing the two figures that we wanted. The first is methane in this zonal mean plot for this region of the atmosphere. Note that the GCHP run that we've plotted on the right has been regridded to 1 by 1.25 degrees for comparison purposes with our GEOS-Chem classic grid. And on the second page we have our ozone plot in the same format as our first plot. So that's it for examples in this video and also the end of this video itself. As I mentioned before, there are many other examples and extensive documentation that can be found on our Read the Docs site, which is linked in the description of this video. It's also got links to where you can open GitHub issues to ask questions, report problems, or request new features be added to GCPy. Besides that, that's about it. So thank you for watching, and I hope you install GCPy.